We'll now begin the next section. This is section 4.5. This is undetermined coefficients and annihilator approach. So this is an alternative way to solving these linear differential equations with constant coefficients. It's an alternative to the method that we presented in section 4.4. If you honestly get comfortable with either one of the two methods, and if you prefer one versus the other, it doesn't matter to me how you particularly tend to solve them. I will never say that you must use the annihilator approach or that you must use the method we did in 4.4. At the end of the day, if you can solve the differential equation using any means necessary, I will be perfectly happy. But nonetheless, there are some interesting concepts and notations that are kind of introduced in 4.5 that do pay dividends later on in a study of differential equations. So it is important to, kind of appreciate what we're going to do in this next section, even though it doesn't present us anything necessarily new in terms of ability to solve a different style of equation. It does give us a new approach to one we've already seen and solved previously. The first thing that we're going to do is we're going to kind of revert back and change notation. We're going to use the operator form of the derivative. So typically where we would write things like, let's say, y double prime, y triple prime, etc. So typically we would write, using the Leibniz notation, dy dx, or we might even write y prime. We're now going to write d of y. For the second derivative, which would be d squared y dx squared in Leibniz notation, or y double prime, we're going to represent that derivative, that second derivative, using the operator d squared. So using the operator form of the derivative, we can rewrite the left-hand side of our differential equation with constant coefficients as follows. It's a sub n d to the nth derivative, plus a sub n minus 1 dn minus 1, plus all the way down to a1d plus a sub 0. And we think of this differential operator as acting on the function y. And we're now going to come to the concept of factoring operators. So let's suppose that these are real constant coefficients as we've been working with in this section. Then the differential operator can be factored whenever the characteristic polynomial a(n) m to the m plus a sub n minus 1 m to the n minus 1 all the way down to a1m plus a sub 0 when this factors. Okay. So if you can kind of think of, replace the d's with like m's, and if that resulting polynomial factors, then our differential operator will factor as well. One of the fundamental results from algebra is that, let's suppose that r1 would be an auxiliary root of this equation. If r minus 1 is a root, then that would mean that m minus r1 would be a factor, or in other words, we could write the differential operator L could be written as d minus r1 times p of d, where p of d would be a polynomial differential operator of degree 1 less. Okay, that was kind of the fundamental theorem of algebra. Now we're seeing it manifest itself in differential equations. Okay. As an example, if we had the differential operator d squared plus 5d plus 6, if you just kind of treat the d as if it was like an x variable or y or m, like back when you learned how to factor, this expression would factor as d plus 2 times d plus 3, or, algebraically, we know that the property of multiplication is commutative. It would also factor as d plus 3 times d plus 2, but you have to be a little bit careful here, because this isn't necessarily just, an algebraic expression. We're viewing these as operators. So you should, at some level, question, as an applied operator, would this expression give us the same result as this expression if we apply it to a function y? And the answer is yes. So differential operators, linear differential operators that are factored like this, they do commute. So whenever you factor this thing, it doesn't matter which order you write the factors of your differential operator, they will act on functions the same way. So if I take that original differential operator and apply it to a function y, if it's in factored form, it doesn't matter which order you write the factors, the resulting expressions will be the same. Okay, so very important, nothing to worry about, something we're kind of used to from previously. But not all operations in mathematics commute. Fortunately, this does. And of course we have a repeated factor. If you look at the differential equation, y double prime plus 4y prime plus 4y equals to 0, we can view this in operator notation. We can think of this as the second derivative plus 4 times the first derivative plus just 4 times the function y. So the differential operator would be d squared plus 4d plus 4, and that's applying to the function y. This would factor. It actually factors with the repeated root. We have d plus 2 times d plus 2, and of course we can write the exponential notation, the operator d plus 2 squared, applying to the function y. This brings us to the concept of what we call an annihilator operator. Let's suppose that L is a linear differential operator with constant coefficients, so L is of this expression. So let's suppose that L equals to an expression of this form. We say that the linear differential operator with constant coefficients, if we apply it to a function f that has all of the required derivatives, if the differential operator applied to the function produces the result of 0, then we refer to L as being an annihilator of the function. Okay, so notice that we say an annihilator, not the annihilator. There can be more than one differential operator that in particular can annihilate a function. For example, if we take the constant function y equals to k, we know that the first derivative would turn this into 0. So if I take the derivative of any constant, that's the first thing, one of the first things you learn in Calc 1, we know that that derivative is going to be equal to 0. Okay. I could have taken the second derivative of a constant, the third derivative, any higher order derivative also would have annihilated y equals to k. If we look at the function y equals to x, the first derivative would give us 1, but then if we take the second derivative, then we would have 0. So we could say that the function y equals to x would be annihilated by the differential operator d squared. Because if we apply d squared to y, we get the first derivative would be x, so it would be 1, the second derivative would be 0, and so that would annihilate that function. Similarly, the differential operator d cubed, d to the fourth, or any higher power of d would also annihilate y equals x. Okay. If you wanted a differential operator that's going to be an annihilator for x squared, well, if we have a polynomial of degree 2, and if we take 3 derivatives, then that will result in 0. So it's really kind of quickly easy to figure out what types of things would annihilate powers of x. If you have, let's say, x to the n power, or in this case x to the n minus 1 power, then the next higher order for the differential operator will be an annihilator for it. So for example, we saw that a first degree power of x was annihilated by d squared. A second power of x was annihilated by d cubed. So d to the n, this differential operator, would annihilate any lower power of x. So it annihilates the constant term 1, it annihilate x squared, and it would annihilate all the way up to x to the n minus 1. It also, because of the linearity of the differential operator d, dn would also eliminate this entire polynomial. The functions that are annihilated by a linear nth order differential operator are simply those functions that can be obtained from the general solution of the homogeneous differential equation L of y equals to 0. So the operators that we're kind of coming from are in many ways kind of similar to things we saw in the past, where they're the general solution of the homogeneous linear differential operator L of y equals to 0. The next thing we're going to look at is let's think about what kind of things would eliminate or annihilate polynomials times e to a power. To see what would be an annihilator for this, let's kind of work backwards. So if you think about solving, let's say, the homogeneous differential equation d minus alpha to the n y equals to 0. So remember back whenever we had a repeated root from section 4.3, whenever we had a repeated root, we needed the solution to be of the form e to the mix, and then for every time that root got repeated, to make things linearly independent, we had to add additional powers of x. Well, same thing kind of here too. So if that's the case, then we know that this differential operator, this would be a solution, a general solution to this homogeneous differential equation, which means that d minus alpha to the n would be an annihilator for each of those functions. So if you have a polynomial times e to some power of x, then the operator d minus the coefficient of the x variable in e, and then the order of it has to be one more than the polynomial order that's multiplying to the e. So let's say if I had like x cubed, let me give you an example of this. So let's say, for example, if I had x cubed e to the 10x. The differential operator that would work for this, so the rule of alpha would be the number 10. So it's going to be d minus 10. And then for the exponent that we're going to need here, notice that the exponent is simply going to be one more than that highest power of x. So if this is x cubed, then I would need a fourth power here. And it would work very similarly if I had a more general thing. Let's suppose I have like 5x to the 6th minus 3x to the 4th plus 7 e to the 9x. A differential operator that would annihilate this entire expression is going to be d minus 9. And this is a polynomial of degree 6, so I would need a 7th order differential operator. So d minus 9 to the 7th would annihilate something that looks like this. Let's get a little bit of practice with this. In example 1, we want to find a differential annihilator that annihilates each function. So for the first part, we have 1 minus 5x squared plus 8x cubed. It's a polynomial of degree 3, so I claim that the differential operator d to the fourth derivative, should annihilate this. Let's go ahead and check. Not going to do this every time, but since we're just kind of new to differential operators, it doesn't hurt. And again, you can think of this fourth derivative as, you know, successive differentiation. After all, we know from Calc 1, if we're going to find the fourth derivative, then we have to start off by finding the first derivative in particular. So when we do our first derivative, that's going to produce negative 10x plus 24x squared. We now take the second derivative, differentiate again. That's going to give us negative 10 plus 48x. Differentiate a third time, we get 48, and then differentiate one more time, and we get 0. So as we said, this differential operator d to the fourth would annihilate the polynomial 1 minus 5x squared plus 8x cubed. Take a look at part B. We want to find a differential operator that would annihilate e to the negative 3x. So we know that it should be of the form, according to the notes, it's going to be d minus alpha to the n. This is going to be d Alpha is negative 3, so minus a minus 3 will be plus 3. And then it's one more power than the power of x you would see out in front of this. Well, if there's no x, in other words, if it's a constant, then that would be like x to the 0th power. So the operator should be just d plus 3. So the linear operator d plus 3 should annihilate y equals e to the negative 3x. Let's go ahead and apply this. If we take and apply d plus 3 to e to the negative 3x, you can distribute. This is going to be the derivative of e to the negative 3x plus 3e to the negative 3x. The derivative of e to the negative 3x is negative 3e to the negative 3x plus 3e to the negative 3x. Sure enough, those two terms cancel, and so as we said a moment ago, the differential operator d plus 3 would annihilate e to the negative 3x. Take a look at one more, and it might be helpful for this one. I'm just going to kind of rewrite it. Here, I can factor out the e to the 2x so that it really looks like a linear polynomial times e to the 2x. From what we just said a moment ago, a differential operator, I'll call it L, that should annihilate this thing, is it's going to be d minus the coefficient of the x and the e. That's going to be d minus 2. And if we have a linear polynomial, then the order of this differential operator has to be of degree 1 more. So polynomials are linear functions are polynomials of degree 1, so we need a differential operator of degree 2. So the differential operator that should annihilate this expression would be d minus 2 squared. Let's actually go ahead and check this. Just in case if any of you are skeptical out there, I wouldn't blame you, but trust me, it does work. So we want to apply the differential operator d minus 2 squared to the function 4 e to the 2x minus 10x e to the 2x. We can think of this as d minus 2 times d minus 2. It's a repeated factor. So we're applying the differential operator d minus 2 twice. If I apply it the first time, again, it distributes. We're going to have the following. We're going to have d minus 2. My d's and my parentheses are kind of blending in here a little bit here. Let's see if I can clean up the penmanship. We need to apply that to 4e to the 2x. Actually, let me perhaps do it like this instead of being silly. So we need to take the derivative of the thing on the inside. And we also need to subtract twice the function on the inside. That's how this differential operator behaves. So we have d minus 2. It will be applied to the result of this. If I take the derivative of this expression, we're going to get 8 e to the 2x for the first part. This is going to be a product rule. We have negative 10 e to the 2x. And then this will become a minus 20 x e to the 2x. Distributing here will give us a negative 8 e to the 2x plus 20 x e to the 2x. Before we apply d minus 2 again, let's see what happens. We get a bunch of cancellations. 8e to the 2x and negative 8e to the 2x cancel. the negative 20x e to the 2x. And where'd that square come from? That shouldn't be there. And the positive 20x e to the 2x cancel. So what we're left with right now is the following. We're going to apply d minus 2 to negative 10 e to the 2x. That is, we need to take the derivative of negative 10 e to the 2x and then subtract twice that function. The derivative of this would be negative 20 e to the 2x. This is a positive 20 e to the 2x, and sure enough, it does simplify to 0. So the differential operator, d minus 2 squared, would annihilate the function 4e to the 2x minus 10x e to the 2x.